We are very much excited to share our new results on the experimental and analytical modeling of cement-based products carbon uptake with you today. First, I would like to thank our collaborator here, Concrete Masonry and Hardscape Association, who have been helping us collecting the data and also implementing the experimental design that we have come up to share these exciting results with you. So I will start this presentation about the importance of carbon uptake and the trend that we have seen over the past few decades, particularly as you can see on this graph from 1960, we have more than 30% growth in the CO2 concentration level in the atmosphere. This will change the equilibrium of the CO2 uptake and CO2 emissions in the atmosphere and therefore ends up with global warming issues. But there are three major sinks of carbon that we can see in our planet. First one is about the ocean carbon uptake, then about different sources in the land, for example, forests, and finally, cement-based products carbon uptake is the third category that we spend most of the time today to discuss with you today. During their last review and within the most recent updated version of the IPCC report, it was stated that carbon uptake in cement-based products and in concrete is a significant sink, which has resulted in about half of the carbonate emissions sequestration from the cement production. We know that it's a generally crude number, but we would like to discuss with you what we can do to make sure that this number is accurate and is context specific. To that end, we have identified several research gaps here that we can use to improve the values and methodologies discussed in different standards and guidelines. First of all, the first gap that we have identified is about the reporting standards, the baseline and time frames that were discussed in those to make sure that we have a harmonized and consistent way of reporting carbon uptake across different types of cement-based products. The second gap that we have identified is about the CO2 variation and CO2 concentration in the atmosphere. Because the carbonation rate is as a function of the CO2 concentration, we need to take this important factor into account when we are thinking about the projections and forecasts of the carbon uptake in cement-based products in the future. The third research gap is that generally the cement-based products are made and are finally used in different buildings and infrastructure systems in a multiple layer format. It's either covered with a layer of finishing or paints, and these will impact the rate of the carbon uptake significantly. So the question that might arise here is, if we want to have a more accurate estimation of the carbon uptake at the element, building, or the global or national level, what would be the best way to take into account the impacts of layers and having the analysis more context specific? And the last part is about the casting method. There are different types of cement-based products, including wet cast concrete or dry cast concrete. And the system in general, the porosity of the system and the physics of the systems are quite different in these two different products. Where in wet cast, we have a very smooth surface and homogeneous and isotropic environment and medium. In dry cast, we see coarser pores and we see a lot of different inhomogeneity in the mixture. So we need to take into account these important factors when we are assessing the impact of carbon uptake. Our today's presentation mostly focuses on the difference between wet cast and dry cast and what we have learned so far from the experimental and analytical studies. With that, I would like to stop here and I would hand it over to Pranav to continue the presentation and discuss the methodology and the findings of this research. Pranav, please take it away.
Sure. Thank you, Hessam. So, as Hessam mentioned, we aim to improve the context specificity of carbon uptake models by accounting for different casting methods. So for today's webinar, I will be focusing on the casting method and would like to walk you all through our work on carbon uptake modeling of dry cast manufactured concrete products. Therefore, the main research aim here is to develop multiple analytical models to estimate the carbon uptake behavior of dry cast manufactured concrete products. And to build these models, we start by collecting and analyzing long-term experimental test data on carbon uptake in dry cast concrete over time, followed by developing element-level analytical models to predict carbon uptake of dry cast concrete. And then we extend our context-specific model to calculate the uptake of dry cast concrete wall system. And finally, we conduct a full life cycle carbon analysis of a CMU wall to quantify its true net CO2 emission. The key messages that we have learned from this study are as follows. Firstly, the dry cast carbon uptake is faster at early ages. Second, maximum practical carbon uptake observed in dry cast concrete is approximately 55%. Third, the current standards underestimate the dry cast carbon uptake. Fourth, life cycle carbon uptake of dry cast concrete walls sequesters approximately 24% of the total wall emission. So first, let's look into how carbon uptake in dry cast concrete looks like. So in order to understand the carbon uptake in dry cast concrete, an experimental testing was conducted in collaboration with Concrete Masonry and Hardscapes Association. The sampling and uptake measurement were performed from 28 days to 1,240 days, which is approximately 3 years in these dry cast manufactured concrete masonry units, which are CMUs. Firstly, there's casting and storage, where the CMU blocks were produced under plant conditions, and they were stored according to the different exposure scenarios. Then the sampling was conducted at different scheduled ages, as shown in this table here. The test ages started from 28 days to 90 days to 180 days, all the way through to 1,240 days. So we collected data from 1 month, 3 months, 6, 9 months, then 1 year, 1.5 years, 2 years, and 3 years. And finally, the CO2 measurement was conducted using a thermogravimetric analysis, or a TGA analysis, at a temperature ranging between 550 to 950 degrees Celsius. And in order to improve the efficacy of the carbon uptake modeling in dry cast concrete system, 2 initial exposure conditions were considered here. The first one, which is represented as EXP1, or exposure 1, where the blocks remained in an outdoor condition from when it was cast until the test day. And the second exposure condition, which is represented as EXP2, where the blocks spent the initial 40 days after casting in an outdoor condition before they were moved into a semi-indoor environment for the remainder of the period until they were tested. And this design helps in understanding the early age as well as the long-term carbon uptake effects on dry cast concrete, as well as it also helps us in understanding the influence of initial curing environment on these dry cast CMU blocks. So from the TGA analysis, we get the total amount of carbon dioxide sequestered with respect to the total weight of the samples that were considered. And when we multiply this value with the density of the different blocks, this will give us the total carbon uptake per unit volume, as shown in this figure, where the y-axis here represents the carbon uptake in kilogram CO2 per cubic meter of concrete. The red data points that you see here represents the EXP1, or the outdoor environmental condition, with testing conducted up to 3 years. And the blue data points that you see here represent the EXP2 condition, with testing conducted up to 1.5 years as of today. Another way to express the carbon uptake is as the percentage of calcination carbon emissions of the cement that was used in the CMUs. for which the CO2 value that we get from the TGA analysis is divided by the calcination emissions associated with the CMU as shown in this figure. Here, the y-axis represents the carbon uptake as the percentage of calcination emissions. And we observe that irrespective of the exposure conditions, both the data sets follow a logarithmic trend as opposed to a square root of time relation, which is used for modeling wet cast concrete. And this highlights the need for context-specific modeling for different casting methods, primarily because in dry cast, particularly at the early ages, along with the diffusion, there is capillary action as well. And the capillary suction drives the transportation of the carbon dioxide ions that were dissolved in the moisture, forming a suction gradient as opposed to the concentration gradients in wet cast. Thus, the diffusivity in dry cast concrete is not a constant value. The red and the blue bands here represents the 95% confidence interval range for the model that we have adopted for the two experimental exposure conditions. And on average, we see that the CMUs can sequester approximately 48% of the calcination carbon emissions of the cement over a period of 3 years for the EXP1 or the outdoor condition. And approximately 35% is sequestered over a period of 1.5 years for the experimental 2, as opposed to 42% for the experimental 1. So we see a slight difference in the amount of carbon dioxide, amount of carbon that has been sequestered into the dry cast concrete blocks with respect to the two exposure conditions that we considered. And this highlights how initial exposure condition plays a crucial role in carbon uptake calculations. Next, let us look into the maximum practical carbon uptake. In order to understand the maximum practical carbon uptake in dry cast concrete systems, once again, we conducted an experimental testing on crushed dry cast concrete samples. The sampling and uptake measurement were performed from 128 days to 600 days after they were crushed. And there was carbonation happening before this period as well, but the testing was conducted from 128 days to approximately around 600 days. Firstly, the CMU samples or the CMU blocks were crushed, and followed by they were graded and they were sampled for the different ages of testing, starting from 128 days through 600 days. And finally, the CO2 measurement was conducted using the TGA analysis, similar to what was conducted for the dry cast concrete blocks that I explained in a couple of slides back. Here, from the results, we observed that similar to the CMU blocks, the crush data obtained from the TGA analysis gives the total amount of CO2 sequestered by the crushed samples with respect to the total weight. And here, the y-axis represents the carbon uptake as a percentage of the calcination carbon emissions. And the data here shows a nearly straight line. The average line is nearly a straight one from 128 days to 600 days, indicating that the crushed samples have sequestered the maximum practical uptake, which is approximately 55%. This value is much lower than the degree of carbonation value for the wet cast concrete, primarily because the dry cast concrete does not allow for a full dispersion of the cement particles due to its low moisture content, and typically about 25 to 35% unhydrated cement particles, indicating that the crushing operation is not intended to expose the unhydrated cement particles inside the cement agglomerations that happen due to the less moisture content or less water to cement ratio used in dry cast concrete units. Next, let us consider an example to evaluate the carbon uptake using current standards along with the developed model. So here, let's consider an example of a CMU wall as shown here, which is about 15 foot by 9 foot, that is made up of a standard concrete block, which is 16-inch long, 8-inch wide, and 8-inch deep. The strength of the CMU is taken as 25 megapascals with about 200 kilogram per meter cube of cement. And the service life of the wall is taken as 50 years with an outdoor exposure condition exposed to rain. And we considered two methodologies to calculate the carbon uptake in this concrete CMU wall. The first method is based on the EN 16757 standard. Here, using the exposure condition that I mentioned, which is the outdoor exposed to rain condition, and the strength of the concrete, the degree and the rate of carbonation can be taken from this standard. So for this particular example, the rate of carbonation is taken as 1.6 millimeter per square root of year, and the degree of carbonation is taken as 85%. And the method two, which is based on the analytical model that we developed in this study. And since it's an outdoor exposed to rain condition, we have considered the EXP1 model line, which is represented by the red line that you see in this plot here, which closely represents the outdoor exposed to rain exposure condition. And see that here, once we conduct this analysis, this plot here shows the carbon uptake obtained using the approach described in the EN 16757. Here, the y-axis represents the use phase carbon uptake, that is the kilogram carbon dioxide uptake per unit area of the wall. So it's kg CO2 per meter square. And this approach gives an uptake of approximately 4 kg CO2 per meter square that can be observed in the bar plot on the right-hand side at the end of the 50-year service life, with just about 0.14 kg CO2 per meter square that is sequestered during the storage period of the CMU or during the curing period of the CMU units, highlighted by the dark brown bar chart. However, if using the EXP1 analytical model that was developed in this study, it can be observed that the use phase carbon uptake is approximately 5 kilograms CO2 per meter square. The significance of this model is the improved accuracy of the uptake estimates at the early stages. And you can observe that in the first 5 to 10 years of the life cycle of this particular CMU wall, we see that the analytical experimental 1 model captures a significantly higher amount of use phase carbon uptake as opposed to the carbon uptake that's observed in the observed using the EN 16757 model. And we can also see that at early ages, the EXP1 analytical model sequesters about 1.83 kg CO2 per meter square during the storage phase, which is significantly higher than the 0.14, which is estimated using the EN 16757 standard. And this highlights the importance of capturing the early age carbon uptake in dry cast concrete products, which the square root of time approach adopted in the EN 16757 systematically misses. And followed by, we conducted a life cycle analysis for the CMU wall to quantify how the carbon uptake neutralizes its life cycle emissions. For the life cycle analysis, we considered the functional unit as 1 square meters of the CMU walls for a 50-year life with a system boundary that includes A1 to A3 production emissions, B1 use phase emission, and C3, C4 end of life emissions. And for the case study, we considered a wall that is exposed to an outdoor unsheltered or exposed to rain condition. And the wall comprised of standard concrete blocks with 16 by 8 by 8 inch blocks with a strength of 25 megapascals and a cement content of 200 kilogram per meter cube. And we also considered a type M mortar with a strength of 17 MPa and a cement content of 350 kg per meter cube. Once we conducted the analysis, the plot here shows the results from the life cycle analysis, where the y-axis here represents the life cycle emissions, which is kilogram CO2 per square meter of the wall. The analysis shows that the A1 to A3 emission here is approximately 21 kg CO2 per meter cube, with about 9.1 kilogram CO2 per meter cube associated with the calcination emissions of both the blocks as well as the CMU blocks, as well as the mortar that was used in the case study example. And we also considered the storage phase, which was calculated using the EXP1 analytical model, where we got that the A3 storage emissions approximately gives 1.83 kg CO2 per 1.3 kg CO2 per meter square is neutralized in the first 28 days of storage or the curing phase of the CMU wall. And then we calculated the use phase carbon uptake, which further neutralizes another 3.17 kg CO2 per meter square of the emissions, the total emission of the wall that we are considering here. And finally, there is very small amount of end-of-life emissions that has been neutralized by the CMU walls, primarily because most part of the carbon uptake has been sequestered, or the carbon dioxide has been sequestered in CMU units in the first 10 years, as was observed in the plot that I showed a couple of slides back. And what this gives is that at the end of the 50-year life of the CMU wall, the net carbon dioxide emission is about 15.9 kg CO2 per meter square, which is roughly about 24% reduction with respect to the initial total emission for the CMU wall that was considered in this case study. And therefore, some of the key takeaways from the analysis that we conducted here is that the dry cast concrete follows a logarithmic carbon uptake curve as opposed to the square root of time curve that is observed in wet cast concrete. And therefore, the models must account for its unique casting method and the pore structure and the pore characteristics specific to dry cast concrete systems. The second takeaway is that the crushed CMU tests show dry cast units can sequester up to 55% of their calcination emissions when exposed to the outdoor environment, which can be considered as the maximum practical carbon uptake limit for the dry cast units. Thirdly, the current standards and reports overlook the rapid early age carbon uptake of the dry cast mixes, leading to a systematic underestimation of uptake in these products. And the fourth takeaway from this study was that over a 50-year service life, a dry cast wall can neutralize roughly about 24% of its total CO2 emission. And this underscores why capturing the uptake in life cycle assessments is essential for credible life cycle carbon analysis. And moving forward, some of the future works are listed here, such as developing a dynamic carbon uptake model for dry cast manufactured units by integrating the environmental data such as temperature, humidity, and carbon dioxide concentration. Second, a development of guidelines to include carbon uptake in environmental product declarations. Recently, a paper in collaboration with the Concrete Masonry and Hardscapes Association was published at the 15th Canadian Masonry Symposium, which has some guidelines on how to use the model equations to calculate the carbon uptake of CMU at various ages. And the PCR Development Committee plans to include some of the some guidance in the new PCR that will be coming out later this year. And third, we plan to implement the same framework from CMU. We would like to extend it to other dry cast products like the concrete paving units. And fourth, we also plan to conduct a digital image analysis on different profile samples of these CMU units. So while we have started addressing the fourth gap for the dry cast masonry units that is shown here, the other three gaps can also be applied to masonry and other cement-based products. And we also plan to integrate this into the dry cast concrete analysis as well. And that brings me to the end of this presentation. Thank you, everyone.
Well, thank you very much, Pranav. As you have seen, there's a lot of difference that you can observe in dry cast in terms of the structure, the skeleton of the blocks compared to the other cement-based products, and therefore the carbonation behavior is totally different in these blocks. And we can see that there is a significant amount of carbon uptake sequestered over the manufacturing timeline, as well as the use and end of life of the CMU units as well. Great. So we have a few questions in the chat box. Please feel free to pose your questions. I'm going to start with a more general question, Pranav, about the difference between the carbon uptake in cement-based products and the carbon capture, for example, the carbon capture and storage, or similar technologies. How would you differentiate this? Could you give us a little bit information about the fundamental of the carbon uptake and how it differs from carbon capture and sequestration?
Yes. So the carbon uptake that we have discussed here is the natural mineralization of the CO2 in cement-based products, which is defined as the carbonation mechanism that often happens in concrete products or any cement-based product. And this happens due to the presence of calcium hydroxide that's present within the concrete products, and the carbon dioxide reacts with the calcium hydroxide present within these cement-based products to form calcium carbonate, and that's how the natural process of cement-based products, how it absorbs the CO2 from the atmosphere into the carbon dioxide, and it stores it permanently within the concrete products. In the carbon capture technology, primarily it's more of taking the carbon dioxide in a more man-made fashion into the concrete, as opposed to the natural mineralization that is observed through the carbonation process within the carbon uptake mechanism that has been shown in this study and the presentation.
Perfect. So based on your explanation, the main difference is in carbon capture and sequestration, the carbon is sequestered in a significant I don't know, tank, or it's gonna be piped. But in carbon uptake in cement-based products, we see that the CO2 is permanently stored and mineralized actually in the cement-based products in general.
Absolutely. And
Great.
also it takes a long time for it to get mineralized.
Question about, I know you haven't shown these results and you're still working on that, Pranav, but there's a question about the profile, the penetration depth as a function of time. And do you think that it is getting slower over time due to the densification of the carbonated surface? How does this differ? If you can, say, I know you didn't include the results, but please feel free to say that.
Yes, so we are also performing an analysis on the different profiles within the CMU blocks, where we are considering like about 6 millimeter thick profiles to see how the carbonation has progressed over time at different 6 millimeter levels. And from our preliminary observations, we see that over time, the top layer, or the top 6 millimeter layer, absorbs a significantly higher amount of carbonation in the first 28 days, as opposed to the following 6 millimeters or the following 12 millimeters into the CMU blocks. And thereby we see that the carbonation depth or the penetration depth is higher in the early ages. It's only in the first 6 millimeters, and then the penetration or the rate of penetration significantly drops, and it slows down with respect to time. So yeah, yes, it is high in the initial few days, and it slows over time due to the densification of the carbonated surface.
Perfect. So the logarithmic behavior that he showed, that we have a significant jump at the beginning, but we will reach a plateau as we move forward, kind of explains that how the depth would, the densification will change as a function of the depth. Great. Question about the impact of fly ash and slag or other alternative binders. How do you think the carbon uptake results would vary in light of the decarbonization and the replacement of these materials with ordinary Portland cement with slag or fly ash?
Yes. So primarily for the experimental tests that we have conducted here in the CMU blocks, we have not considered other supplementary cementitious materials like fly ash or slag. It only considers the OPC cement. However, if we consider like the fly ash and slag, there would be difference in the results observed if we use calcined slag or the calcinated slag component within the concrete, because that would change the way the carbon uptake or the carbonation process happens within the concrete blocks. But if it is not calcined material, then the model more or less would remain the same, or the same model can be adopted for blocks that are made out of mixes with uncalcinated slag or other SEMs.
Great. So the change in the binder system would definitely change the K value and degree of carbonation. So the rate and degree of carbonation can potentially vary. But the 16 set of blocks that we received their experimental data from the Concrete Masonry and Hardscape Association didn't have any SCMs, but it includes Portland limestone cement. I just wanted to emphasize that the geographical scope of this study is pretty much broad, so more than 1,000 data points so far for different ages and different blocks. But the current practice is mostly based on the minimum amount of SCMs in blocks. But we see the trend that moving forward, there's a chance that we have more alternative binders replacing ordinary Portland cement. Great. Another question. Well, the questions are, we have a lot of questions coming, so I'm trying to kind of prioritize some of them, and I hope we will get a chance to answer all of them. So Pranav, if you could be as concise as possible, I would appreciate it.
Okay.
So there is another question about the carbon uptake of LC3 cement and how it differs from the carbon uptake of ordinary binder systems, which I think it's very well explained, as you mentioned, Pranav, about the impact of the SCMs or different types of alternative binders on carbon uptake. There's another question about the storage of the blocks, which I think it's more a practical question, like what's the reason behind storing the blocks, that holding time that we see before installing those blocks at the construction site? What's your thoughts on that?
Yeah, I think more often, like in practical conditions, they store it for about 28 days as part of the curing process after they are demolded. And the cast system is out in an exposed condition in most cases. And that's one of the reasons why even in our study, in the experimental study here, we have kept these blocks outside to represent a realistic condition of how these blocks are manufactured in practice. So yeah, I think that may vary depending on like how the products are being stored by different plants or different manufacturers, the number of days.
So you're saying that after the blocks coming out of the curing chamber, then they would be stored at the site until the
They're
the
constructed.
new batch comes out, and then it's going to replace that one as the current batch will move to the construction site. So it's a kind of industry practice right now. Is that right?
Yes.
Okay, perfect. Question about the layers, Pranav. Most CMU is painted. How does that affect the carbon uptake of CMU? Or you can put it in the context of general cement-based products, right? Like we have ICF panels, and we have insulation on the outer side of the concrete that is being poured. We have different layers of paints. So how would you see the uptake modeling for that? I know you mentioned that as a part of the future work, but if you could comment on how from a practical perspective and analytical perspective, how can we model that? That would be very helpful.
That's great. Yes. So one of the crucial point here is that when we have a layered system, due to the presence of multiple layers, each of these material associated with the layers have a different diffusivity or diffusion rate of carbon dioxide. So if we have a concrete wall which has a layering of a paint or the ICFs, in front of the surface of the concrete wall, then the carbon dioxide from the atmosphere has to first go through each of these layers before it can reach the interface of concrete and the previous layer. So based on the diffusion rate of these different materials or the layering system, it can slow or increase the speed at which the carbonation happens within the concrete system. And usually when we consider, like, for example, a wall, it has two surfaces, the indoor and the outdoor surface, and both the surfaces might have like different layers. So we could have like painting, or we could have like ICF on one side. And based on this, the carbonation happens from both the fronts. And depending on the difference in the material diffusion rate, the carbon dioxide would rapidly or slowly penetrate into the interface between the concrete surface and the previous material. So that would kind of shift the carbonation curve up or down depending on what material is considered as the layering. But yes, it will have some amount of impact depending on the diffusion rate and the thickness of the layering material.
Coating of the layer, right?
Yes.
So it doesn't stop, but it changes its pace, right? Because the
Yes.
diffusion of the diffusivity rate of the paints are different from the concrete or the block itself.
Absolutely.
Great. About the measurement techniques, there's a question that how can we measure the amount of CO2 uptake that goes into the CNU blocks? Can we measure it by mass, which I guess it's a very relatively imprecise way, but could you explain a little bit about the TGA test?
Yes. So in TGA test, once we take the samples, like be the crushed samples or the CMU coupons, they are initially broken into a small powdered form taken from these samples, and they are kept into the oven which tests the which conducts this analysis, where the temperature is increased from 0 degrees all the way up to about 950 degrees. And at different ranges of temperature, different elements from the CMU samples are removed from the system. And therefore, between 550 and 950, that is the temperature range where the carbon dioxide within these concrete systems are decomposed, and we can see the total weight that we measure at the end of the TGA analysis directly gives the amount of CO2 that was present within the CMU sample that was tested at that particular age. So for different ages, we get different CO2 values that represents the total amount, which is in terms of percentage of the total weight of the sample that was used for the TGA analysis. So the result that we get is a percentage of the total weight, CO2 weight as a percentage of the total weight. And then we could use that value along with any of the properties of the material, like we use the density. When we multiply it with that, we would get the total amount of carbon dioxide captured with respect to the unit volume of the.
Okay, so it's a mass-based technique that would result in the amount of burnt minerals as a result of increasing the temperature for like a relatively smaller sample of the CMUs, but you cannot weigh the block as a function of time to measure the amount of carbon uptake because it's very imprecise.
That's correct.
Okay, next question. How do you think this uptake progress be as a factor of block category, CMU, or pavers? Like, how would you see that the uptake varies between pavers and CMUs?
Yeah. So we are still in the testing phase for the paver units, and what we observe is that even for the paver units, there is a difference as compared to the wet cast concrete. It follows a similar trend, which is different from the wet cast concrete. Between the CMU and paver, the results are slightly different, but the highlighting point here is the trend which it follows. It primarily takes the logarithmic shape or the logarithmic relation with respect to time, as opposed to the square root of time observation that's done that we observe in wet cast concrete.
Great. One more question about carbon sequestration of the wall that you calculated using the LCA framework that you developed. What components did you consider, and was masonry grout part of those that you included in the carbonation?
No, it was only the masonry blocks and mortar, just the
Mortar.
mortar part. Yes, we
Okay.
included the mortar.
We know that it might vary from one place to another when we think about the masonry walls as the structural elements of a building, particularly in hazard-prone areas. We see that there's grout every 2-3 feet of the wall. So grout can or cannot be part of that. So we can develop, but your model is capable of measuring the amount of carbon uptake of the grout as well, right?
Yes, it is.
Again, we can think about it as a multi-layered system. So the first layer is the CMU, and then the next layer, which has a new mixture, meaning that new compositions of the materials and obviously strength, then this can vary as a function of the depth, and therefore we would be able to calculate the carbon uptake of this layered system as well. Awesome. There is another question about the impact of relative humidity. Have you monitored the relative humidity in the blocks, since in very low humidity or very high humidity, the carbonation is very slow?
Yes, so we currently do not have the full data, but we are recording the temperature, carbon dioxide concentration, and humidity for the CMU blocks. And we are yet to conduct that analysis since the full data has not been available yet. However, it is from literature, we can see that for a lower value of humidity or for a significantly higher amount of humidity, which would be somewhere between the range of 55 to 70% or 55 to 65% of humidity would be the ideal condition for maximum carbon uptake, whereas anything beyond that or lower than that, lower than 55 or higher than 70% could slow down the process of uptake within the dry gas systems. But we are waiting to get the data to kind of corroborate the results and integrate that as part of our analysis. And that's one of the future works that we have.
Great. So as you showed in the logarithmic curves and the curve that you fitted over there, we have an empirical model that we can estimate the amount of carbon uptake. But moving on to a more physics-based model based on the climate parameters, for example, humidity, temperature, after collecting those data, we would be able to have a more physics-based model to be able to estimate the amount of carbon uptake based on the exposure condition and local climate as well. Great. Talking a little bit about the experimental program, is the 0 point for carbon uptake established with the same test as was used to over time? Like so we need a benchmark to compare the amount of carbon uptake. And the question is that, did you use the same test to estimate the amount to measure the amount of carbon uptake compared to the beginning of the block manufacturing, so day 0, let's say?
Yes, so The carbon uptake in the materials, that there could be some amount of carbon uptake in the background that happens within the material before they were cast, and they were recorded and calculated before casting the units. And once they were cast from day zero, the calculation was conducted and the background amount was removed from the measurement that was taken from the TGA. So for the analysis, we have used that net amount from day zero to the 28 day that we tested to calculate what the 28-day value was.
Okay, there's one question. Do you have the data published somewhere?
No, we don't have the data published yet. We have a conference paper that we published, only the experimental 1 condition. So we have the EXP1 data that is published in the 15th Canadian Masonry Symposium, but that's the only source that we have at this point.
Okay, we can definitely send a link to that publication after this webinar, along with the webinar recording, so everyone can see the data points and the model, and they would be able to use that for their own estimation, either in EPDs, environmental product declarations, or life cycle assessment studies that includes dry cast or wet cast units as well.